Now we consider some important particular cases to understand exactly what this kind of problem lead to. Let's consider the nearly free electron approximation. And within that approximation, let's try to find out the band dispersion relation, energy momentum dispersion relation. If we consider a one-dimensional momentum space, then the momentum axis may be represented like this. This is our k-axis. Let's say this is 0 momentum. Let's draw that with green. This line corresponds to 0. This is pi over a. On this side here, this is minus pi over a. Then here it is twice pi over a. Here it is minus twice pi over a. This is thrice pi over a. This is minus thrice pi over a, and so on. So this is the momentum space that we have drawn. And if we now want to represent the free electron energy momentum dispersion, that would look somewhat like let me draw a bit steeper. That would look somewhat like and on this side it's a parabola. That's what it will look like. Maybe this one represents a better parabola. So I will erase the first part. Which looked more like a straight line. So if we have this kind of a picture, energy momentum dispersion relation for free electron, let's see what we will get for nearly free electron system. Now, if we consider k equals plus minus pi over a, that means this point or this point here, then the energy, the corresponding energy would be represented as E naught equals h cross squared over twice m pi squared over a squared. This is the free electron energy here and here. This is E naught. The drawing is not perfect, so these two energies look not to be the same, but in principle they are the same. The reason that they look to be different is the mistake in drawing. Now if we consider k equals plus minus 3 pi over a, then we will see that the energy equals thrice of, sorry, it would be 9 times of E naught. 3 squared, 9 times of E naught, and it will move on. It will be so many energies that we can calculate for different values of k. Now, one interesting thing to mention is that the green vertical lines that we have drawn here, those are the boundaries of the Brillouin zone. If we consider small strength of a periodic potential for this system, then we can consider two elements in the basis. The basis elements in that case may be represented as, at k equals plus minus pi over a, the basis elements that we are interested in would be psi 1 x, which is a plane wave with k equals pi over a. So the wave function is 1 over square root of L exponential of I pi over a times x, and psi 2, the other value of momentum, minus pi over a. So this wave function is 1 over square root L exponential minus I pi over a x. Now, if we diagonalize the crystal Hamiltonian and want to find out the energy eigenvalues, then we will get something like this, a secular determinant like this, E naught minus E V1 E naught minus E, the determinant of this equals to 0. This is the secular equation that we will have, where V1 is the potential at twice pi over a. This is the Fourier transform of the crystal potential corresponding to the lowest reciprocal lattice wave number. Now, we see that the two-fold degenerate empty lattice states of energy E naught are now split. The corresponding energy eigenvalues would be E naught plus minus V1 absolute value. And the same reasoning holds for the other empty lattice degenerate states at the point k equals 0 and k equals plus minus pi over a. So, if we now try to draw that here, what would we draw? We would draw it, draw the new band somewhat like this. And here it would be a bit higher. So, the next place it is crossing is somewhere here. It will come here. And then it will approach this place, say here. So we can draw another band like this. This kind of a band can be expected. So we can understand qualitatively in the nearly free electron approximation that the origin of the energy gaps of the one dimensional crystal that we have calculated in the context of chronic Penny model, this comes due to the splitting of the two-fold degeneracy of the empty lattice that is produced by periodic potential. So you can see that there is a little gap opened here. So this is the kind of gap that we discussed in the context of chronic Penny model. We can also determine analytically the behavior of the energy bands near the boundary of the first Brillouin zone. So what we have calculated here is just these 2 points. We didn't really calculate this part of the band, I've just drawn it because intuitively you cannot imagine something else, but let's calculate it. Let us suppose that the wave number k is very near to the boundary, but not exactly at plus minus pi over a. It's somewhere a bit away. So the basis function that we have considered earlier, that would change now. We will have psi 1 x equals 1 over square root of L exponential of I pi over a minus delta k times x, and the energy, corresponding energy of this plane wave equals h cross squared over twice m pi over a minus delta k squared, and the other basis function psi 2 x equals 1 over square root of L e power I minus pi over a minus delta k times x, and this has the energy E2 equals h cross squared over twice m pi over a plus delta k squared. So the secular equation would be obtained by the determinant E1 minus E V1 V1 complex conjugate E2 minus E. This would give us the secular equation equals 0. If we have this, then the eigenvalues that can be calculated, E equals half E1 plus E2 plus minus square root of E1 plus E2 squared plus 4 V1 absolute value squared. Now, if we insert in this expression the values of E1 and E2 that we have calculated here, we will be able to write E as a function of delta k as E naught plus h cross squared delta k squared over twice m plus minus half square root of 16 E naught h cross squared delta k squared over twice m plus 4 V1 absolute value squared, and this is given with E naught equals h cross squared over twice m pi over a squared. Now, if we have delta k small within this approximation, we can expand this energy as a function of delta k as E naught plus h cross squared delta k squared over twice m plus minus the absolute value of V1 1 plus 2 E naught over V1 absolute value squared h cross square delta k square over twice m plus many more terms, and if we ignore the other terms, then we can write the effective mass of an electron for the upper and lower energy bands as if we consider m star to be the effective mass, then 1 over m star can be written as 1 over the mass of the electron 1 plus minus 2 E naught over V1 absolute value. You are familiar with the term effective mass. Effective mass means if we ignore the potential and consider that there are quasi-particles that are free with a mass m star, then they can be subject to this potential, weak potential that we have in place. They can be considered free particles with this mass, the quasi-particles with this mass. They are moving in the crystal without the influence of any potentials. For weak potentials, small potentials, and for small values of delta k, we can perform this kind of an analysis to arrive at this kind of an expression for the effective mass of the system, of the quasi-particles. In case of small energy gap, so V1, twice of V1 is the energy gap. If this one is much smaller than E naught, then the effective mass is also expected to be small. Okay, now let's see this picture. So you will see that this picture that we have drawn with black is consistent with what we have obtained. And if we now draw the next band would look somewhat like this, and so on will go on in the first Brillouin zone. So this can be put in the other Brillouin zones as well, but repeating them in the first Brillouin zone gives you the entire picture of the band structure with the gaps that you can clearly see here. If you put it in the other zones, that is also fine. There is no problem in terms of physics, but this is customary. This way within the first Brillouin zone, the band structure is often plotted. That captures every information from every other Brillouin zone. Now, if we consider semiconductors with small energy gaps, then we also find that the effective mass in that semiconductor for electrons is small, giving rise to very high mobility of the carriers.